So today we're going to be all on the Bloch sphere, and we're going to be thinking about moving our qubits around using single qubit gates. So just as a reminder, we describe the state of our qubit by a vector, A0 plus B1, and we can also express that same vector as from Euler's formula as R1 e to the phi 1i 0 plus R2 e to the phi 2i 1. We saw by taking advantage of the idea of the global phase, we can kind of re-express this expression for our quantum state that's kind of in the two-dimensional complex plane to being on the Bloch sphere. So we can re-express our state as psi equals cosine theta divided by 2 times 0 plus sine theta divided by 2 e to the phi I times 1. Where our angles, theta, is the angle from the z-axis, and our angle phi is the angle from the x-axis. So moving from sort of the first kind of descriptions of our quantum state to the second requires a nonlinear projection and a change in coordinates, and that puts us onto the Bloch sphere, which can be a useful way of thinking about what you're doing to your qubit when you start manipulating. So when we think about spin, for example, and applications of moving spins around in things like nuclear magnetic resonance, as we'll talk about next week, working on the Bloch sphere will just make a lot of intuitive sense. Okay, so that expression for our quantum state is great when we have a pure state. So we're at the surface of our unit sphere, and if we're a pure state, it's really easy to understand what's going on. But if we have a mixed state, we want to think about the density operator as we introduced last class. And so there's a really cool way to represent what's going on in the context of the Bloch sphere using the density operator. And so we can write this expression here, which we can call the Bloch vector. And our density operator is basically expressed in terms of a linear combination of the Pauli matrices, which you see on the left, and we'll talk more about today, and the identity matrix. And so to understand how this expression comes about, it's helpful to think about what our quantum state looks like when we're expressing it sort of on the Bloch sphere. So we have the cosine e to the I sine form of our quantum state, our qubit state. And if we want to express the density matrix, then we're going to take the outer product, right? So using the qubit state in this form and taking the outer product, we can just expand it out like I have written here. So we have terms that look like cosine squared theta divided by 2 times the outer product of 0 with itself, etc. So now, what's cool, once you kind of have this all expanded out, you can now rewrite this as a matrix, just to simplify your life. So if you do that, you now have your density matrix, which has cosine squared theta over 2, e to the minus I phi cosine squared cosine theta over 2 sine theta over 2, e to the I phi cosine theta over 2 sine theta over 2, and sine squared theta over 2. I can rewrite this in lots of different ways by kind of simplifying, pulling things out and rearranging. So a simplified version of that is shown here. And then I can kind of go a couple steps beyond that and just keep rewriting this 2 by 2 matrix. And I can get to this form where if I write down equations for how I express x, y, and z in terms of sines and cosines. So x is sine theta, cosine phi. Y is sine theta, sine phi. And z is cosine theta. Then I can write a very simple form of my density matrix shown here. So I have 1 plus z, x minus iy, x plus iy, and 1 minus z. And this is how you kind of back out this block vector form of your density matrix. So this is kind of looking at taking a formal vector that's like, if we call them sigma, sigma x, sigma y, sigma z, then our density matrix is equal to 1/2 times I plus R times sigma, or dot product of R and sigma. So it's kind of fun to go from block sphere density matrix, and you can kind of express, you can express your density matrix as in this block vector form. Okay. So when we're looking at our block sphere, there are 3 basis elements that we will kind of talk a lot about. The basis elements that we've been talking about are the basis elements on the z-axis, 0 and 1. We also have the basis elements on the y-axis. They're I and minus I. And we have the basis elements on the x-axis. We call them plus and minus. So one thing that we might want to do is express the form of these states that are on our x or y axes, plus and minus, or I and minus I, in terms of our 0 and 1 states. So, and we could do this for any pair of points, any orthogonal pair of points in our block sphere, but let's do it for I and minus I for fun. Okay, we have 2 points that we're interested in our Cartesian coordinates. So we have A, which is 0, 1, 0, and we have B, which is 0, minus 1, 0. So if we want to define theta and phi, for A, I guess for A and B, we can take theta equals pi over 2, and for A, we have phi equals pi over 2 as well, and for B, we have, wow, I can't write phi. Phi equals 3 pi over 2. Again, where theta is our angle from the z-axis and phi is our angle from the x-axis. So these are the angles that will get us to those points in the Cartesian plane. And so if we want to go back to our form for our quantum state that looks like psi equals A0 plus B1 in C squared, then we can set A equal to cosine theta over 2 and B equals e to the phi I sine theta over 2. And so that'll get us A equals square root of 2 over 2 and B equals e to the pi I square root of 2 over 2. E to the pi I is just I. So that's just square root of 2 over 2 times I. So now we can write that our state's big A, which we also write as I, is equal to square root of 2 over 2 times 0 plus I times 1. And our other state, B, which we also often call minus I, is equal to square root of 2 over 2 times 0 minus I, 1. So this is kind of how we can map out the whole block sphere and get what our coordinates are relative to our pole states, our z states, 0 and 1. So we just kind of derived these ones. You can also derive plus and minus in the same way. Okay, so in general, in the block sphere, we've kind of seen that we have an orthonormal basis in C squared mapping to two opposite points on the Bloch sphere. And every quantum state on the equator is going to have an equal probability of producing 0 and 1 when I measure it. And the state at the North Pole, 0, has a probability of 1 of yielding 0 when I measure it, and a probability of 0 of producing 1. And those probabilities are reversed for the South Pole state. And for a latitude on the Bloch sphere that's not the equator, the probabilities of collapsing to 0 or 1 are different, but they must add up to 1 still. And the probability of yielding 0 is the same for every point of latitude on the Bloch sphere, and same goes for 1. And you can kind of think of where you are relative to the equator as being more or less likely to collapse to 0 or 1. So if you're in the northern hemisphere, you're more likely to collapse to 0, and if you're in the southern hemisphere, you're more likely to collapse to 1. Okay, let's talk about single qubit gates. So when I start looking at manipulating qubits, you're often going to see it written in this kind of string-like form. So I have my starting qubit. It's in its ground state 0, and I'm going to perform some operation here. It's the X gate, and then I'm going to measure, and I'm going to get some value out. Our gates are always reversible, and that comes from quantum mechanics, as we saw last week. And measurement is going to be our only process that's irreversible. There are, like if you go to QISE or you start playing around with building quantum algorithms, you might come up with kind of fake gates or placeholder gates that aren't reversible, but those aren't sort of the elementary unitary transformations that we're talking about here. Measurement is always going to give us back a 0 or 1, and mathematically we don't really care about how that happens. It's just all about the probabilities. And how we actually perform the measurement in a real system is going to depend on what physical manifestation of our qubits we're using. So are we using photonic qubits? Are we counting photons at a detector? Are we measuring microwave signatures of electronic transitions? Are we measuring EPR, et cetera? So when we look at the common gates that are applied in quantum algorithms, they're sort of all listed here. So we have the Pauli gates, the X, Y, and Z gates. And you can see their corresponding matrices, and we'll talk about what each of these gates does a little bit more. We have the Hadamard gate, which is usually the first gate that's applied in any quantum algorithm. It's what establishes your superposition most of the time. And then we have some phase change gates like SP and T. All right, so let's talk about the X gate. So the quantum X gate has the matrix, call it sigma X equals 0, 1, 1, 0. And it has the property that it flips between 0 and 1. So if I apply sigma X, my X gate, to my state 0, I get a 1. And if I apply my X gate to 1, I get a 0. So we call it a bit flip. And if I have a quantum state that's in superposition, so A0 plus B1, then applying X to that superposed quantum state flips the probabilities for 0 and 1. So it flips A and B. So the probabilities of measuring 0 and 1 end up being flipped. And if we think about the eigenvalues for this quantum gate, they're +1 and -1 for the eigenvectors, plus and minus respectively. So we can also think about what exactly is happening on our Bloch sphere when we're applying this X gate. So the X gate is rotating by pi around the X-axis, okay? we can look at a real 3x3 matrix that performs a rotation about the x-axis. If you've ever taken a group theory class with me, you've seen these matrices before. There are classic rotation matrices that we use in chemistry all the time. So they look like this: 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta cosine theta. There's our vector that we're applying it to, and that rotates around the x-axis. So it leaves the x-coordinate unchanged, and then it gives you y cosine theta minus z sine theta, and y sine theta plus z cosine theta. So if we plug in pi, which is what our x gate is doing, it's rotating about the x-axis by pi, we end up with this simple 3x3 matrix that looks like this: 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Okay, so let's look at an easy problem. So if I want to apply the x rotation matrix to 0, and I'm defining my vector 0 by the Cartesian coordinates 0, 0, 1, and 1, which is defined by the Cartesian coordinates 0, 0, minus 1, show me that doing that using matrices results in a bit flip. And then ask yourself, what happens if instead of applying x to 0 and 1, I apply it to plus and minus? All right, so if I apply this rotation matrix to my vector 0, 0, 1, that gives me back, to my column vector 0, 0, 1, that gives me back the row vector 0, 0, minus 1. And if I apply it to, similarly to my column vector 0, 0, minus 1, I get back my row vector 0, 0, 1. So we flipped 0 and 1. That makes sense. You can tell that that was what was going to happen if we just look at the Bloch sphere. So what happens if we apply the x gate to plus and minus? So here's our x gate. Our coordinates for plus are 1, 0, 0. So it's the x-axis vectors. That gives us back 1, 0, 0. And if we apply it to our minus vector, that's minus 1, 0, 0, we get back minus 1, 0, 0. So as you would expect from looking at the geometry of the Bloch sphere, it leaves these alone. It doesn't do anything. Okay, what about the y gate? So the y gate has the matrix sigma y equals 0 minus I, 0. We can pull the I out if we want. 0, minus 1, 1, 0. And this is called the Pauli Y matrix, and it rotates a qubit by pi around the y-axis on the Bloch sphere, so very analogous to what we just saw for the x-axis. It swaps 0 and 1, and so it's also a bit flip. And it also swaps plus and minus. Think about, it's easy to see from the Bloch sphere, but it leaves I and minus I, which are the points on the y-axis, alone. So if we think about quantum state that's in superposition, A0 plus B1, then applying y to that superposed quantum state gets me to minus bi times 0 plus ai times 1, which I can re-express if I want as e to the 3 pi divided by 2i times b0 minus a1. And from this, we can see that y does a bit flip, and it does a phase flip at the same time. So you can see that from the fact that the probabilities switch and the sign changes. the matrix sigma y has eigenvalues plus 1 and minus 1 for eigenvectors I and minus I, respectively. If, yeah, I already said that. In general, if I have a superposed quantum state, then a bit flip interchanges the coefficients of 0 and 1. And a phase flip changes the sign of the coefficient of 1. So that's just a general definition. So I can just write that in general here for you. All right, so what about the Z gate? All right, so the Z gate has a matrix that looks like this, 1, 0, 0, minus 1. And this is called the poly-Z matrix, and it rotates a qubit by pi around the Z-axis on the Bloch sphere. So it swaps plus and minus, as well as I and minus I, and it leaves 0 and 1 alone. Since Z times Z is identity, the Z gate is its own inverse. And if you rotate by pi and then by pi again, you end up back where you started, so that makes good sense. If I have a quantum state that's in superposition, so A0 plus B1, then if I apply the Z gate to that state, I end up with A0 minus B1. So the probabilities for measuring 0 and 1 don't change after applying Z. They're still A squared and B squared. My quantum Z gate has eigenvalues plus 1 and minus 1 for eigenvectors 0 and 1. And we can say that Z is the observable for the standard computational basis 0 and 1. We can say the same analogous thing about the X and Y for their respective orthogonal basis vectors. Cool. X, Y, Z. Easy. All right, so let's do a problem. Show that applying the Z gate to this quantum state, which is expressed a little bit differently, so as R1 e to the theta 1 I 0 plus R2 e to the theta 2 I 1 results in both a phase flip and a sign flip. So how can I simplify this form of the expression? What can I do to kind of see what the Z gate is doing to my quantum state? Yeah, so we have we can pull the e to the theta 1 I out, for example. We can write it as R1 0 plus R2 e to the pi plus theta 2 minus theta 1 I 1. So when we do that, we can see what happens to our quantum state psi much more readily. Our state is changed to pi plus the relative phase adjusted between 0 and 2 pi. And so this lets us see that it's a phase flip, and so Z is called the phase flip gate. Since it reverses the sign of the second amplitude, it's also a sign flip. All right. So the other quantum gates that we'll talk about today are H, the Hadamard gate, S, the phase gate, and T, the pi over 8 gate. So the Hadamard gate is expressed as H equals 1 over square root of 2 times 1, 1, 1, minus 1. So if I kind of use matrix multiplication and apply H to my 0 state, I get 1 over square root of 2 times 0 plus 1, which is exactly my plus state. And if I apply h to my 1 state, I get 1 over square root of 2 times 0 minus 1, which is my minus state. And by linearity, if I apply h to plus, I'll get to 0, and if I apply h to minus, I'll get to 1. So the Hadamard gate is one of the most frequently used gates in quantum computing. It's usually the first one that you apply in a circuit, and so when you read somebody saying, I put the qubit in superposition, it usually means take the qubit initialized at state 0 in the ground state and apply h. So we can see from what the Hadamard gate does that it's the change of basis matrix. It takes 0, 1 to plus minus on the equator. And it's its own inverse. So once I apply it again, and I get back to where I started. So if I wanted to describe what h is doing to my qubit in terms of the Bloch sphere, so I'm rotating by what, etc., how would you describe it? So it's a 90-degree rotation around y, followed by a 180-degree rotation around x. So it creates an equal superposition of the two basis states, 0 and 1. It's what forms a random input, which is why it's usually the very first thing you do when you start a quantum algorithm, quantum computation. All right, what else can we do? I mean, you can think about any way you want to move around the Bloch sphere, and there's a unitary 2x2 matrix that'll take you there. But the few other ones that are worth mentioning that you'll see quite often in quantum algorithms are other types of rotational gates. So, for example, we can generalize the phase-changing behavior of the Z gate by writing sigma z equals 1, 0, 0, minus 1. We can instead write 1, 0, 0, e to the pi I. And we can, if we want to just be really complete, we can say that that equals 1, 0, 0, e to the phi I, or phi equals pi. So the last form, this is sort of our template for a collection of gates that we give the name R, Z, phi. So this is the form of that general gate. But this is a collection, it's infinite because phi can take on any value you want it to take on. And these gates change the phase of a qubit by some angle phi. I could also write this matrix a little bit differently, and sometimes you'll see it written a little bit differently. So I could multiply my matrix by e to the minus phi I divided by 2, and I'll end up with the matrix e to the minus phi I divided by 2, 0, 0, e to the phi I divided by 2. Again, it doesn't matter because multiplication by e to the phi I isn't observable when we measure it. but it'll sometimes make it more convenient to use it in that form. Okay, what about the quantum S gate? So the S gate is shorthand for the RZ pi over 2. So after applying, the phase is adjusted to be greater than or equal to 0 and less than 2 pi. And we can write the matrix as S equals RZ pi over the 2, which is just equal to 1, 0, 0, e to the pi I divided by 2, which is just equal to 1, 0, 0, I. So the S gate is usually known as the pi over 4 gate, which is kind of confusing. And that's because we can express the matrix in this way. So we could multiply the whole thing by e to the pi over 4 and get out, an equivalent form of the matrix. Again, that factor, e to the pi over 4, doesn't have any observable effect on their quantum state and the result of applying the S gate. So sometimes you'll hear people call this another form of a phase gate, but pi over 4 is the more common terminology. Okay, the T gate is the pi over 8 gate, and it's shorthand for the RZ pi over 4. So analogous to what we just saw for the S gate, the T gate, RZ pi over 4, is just equal to 1, 0, 0, e to the pi I over 4, which is equal to 1, 0, 0, square root of 2 over 2 plus square root of 2, 2. You can get the S gate by applying the T gate twice. So S is just equal to T dot T. And the T gate is also known as the pi over 8 gate. So when you hear people say that, that's what you should think. And that's because, again, we can put the e to the pi over 8 out front, and it doesn't change anything about what happens with our T gate. So all of the gates that are on this slide, you might also see them as their adjoints. So instead of a T gate, you could see the T adjoint gate, and that matrix is just the adjoint of the T gate. All right, so we can also define gates that rotate around X and Y in general. So just as the r to the z phi is an arbitrary rotation around the z-axis, we can define our r to the x phi as a generic rotation around the x-axis. That's going to look like cosine phi over 2 minus sine phi over 2i minus sine phi over 2i cosine phi over 2. And you can do the same thing for y. So r to the y phi equals cosine phi over 2 minus sine phi over 2 sine phi over 2 cosine phi over 2. We can also express these in terms of the Pauli matrices. So we could write r to the x phi as cosine phi over 2 times I squared minus cosine phi over 2 times I to the sigma x, the x gate. We can also express the y gate as cosine phi over 2 times I squared minus cosine phi over 2 I to the sigma y, the y gate. So these are just other ways to formulate the X and Y rotation gates. Okay, the last gate that we'll mention is the quantum NOT gate. So you'll see this written as the quantum square root of NOT gate. Sorry, you'll see this written as square root of NOT, and it has the matrix 1/2 times 1 plus I, 1 minus I, 1 minus I, 1 plus I. And what's fun is if you square this, you get 0, 1, 1, 0, which is just the X gate. So the X gate is the quantum version of the NOT gate, right? And so that's how this gate gets its name. So the square root of NOT gate is the square root of the X gate. Maybe I can have you guys for the last few minutes of class, why don't you show that the square root of NOT gate is unitary and find its determinant. And answer the question, what does it do to 0 and 1? So what do we need to do to show that the square root of NOT gate is unitary? So we need its adjoint equal to its inverse. So what's the adjoint of this matrix? So it's just 1/2 times 1 minus I, 1 plus I, 1 plus I, 1 minus I. Is that right? And what's its inverse? Same thing. Okay. What's the determinant of the square root of NOT? Same thing, right? Cool. All right. So that's our quick tour of the Bloch sphere, and basically, that's just about all the gates you'll see. They don't get harder than that. Sometimes you'll see a few other gates introduced, like I mentioned. For example, the quantum reset gate. This isn't a reversible unitary operation in it, but it kind of is supposed to set your circuit back to 0. And that operation can kind of be useful, but it will make your code non-portable, which